From the first moments humans looked up at the night sky, we've been captivated by the stars. We dreamed of exploring the cosmos, of journeying to distant worlds. Then we invented the rocket engine, a powerful machine that could finally defy gravity and propel us into space. Rockets are marvels of engineering, harnessing the fundamental laws of physics to achieve incredible feats. But how do these incredible machines actually work? The answer lies in understanding the concept of thrust, the force that propels a rocket upward. This fundamental law of physics states that for every action there is an equal and opposite reaction. In the context of a rocket, this means that when a rocket expels hot gas out of its engine, the gas in turn exerts an equal and opposite force on the rocket, propelling it forward. Imagine a balloon filled with air. If you let go of the balloon's opening, the air rushes out, and the balloon flies off in the opposite direction. This is a simple demonstration of Newton's third law in action. Rockets work on the same principle but on a much grander scale, using powerful engines to generate tremendous thrust. To truly grasp the mechanics of rocket propulsion, we must delve deeper into Newton's third law. Imagine yourself standing on a skateboard holding a heavy bowling ball. If you throw the ball forward, you'll notice that you roll backward on the skateboard. This is Newton's third law in action. The force you exerted on the ball to throw it forward, the action creates an equal and opposite force that pushes you backward, the reaction. Inside the engine, a controlled explosion creates hot expanding gas. This gas is forced out of the rocket's nozzle at high speed. The faster the gas is expelled and the greater its mass, the stronger the thrust generated. Now that we understand the fundamental principle behind rocket propulsion, let's explore the heart of the matter, the fuel that powers these incredible machines. Rockets require immense amounts of energy to break free from Earth's gravity and propel themselves into space. This energy is derived from the combustion of propellants, a carefully chosen mix of fuel and an oxidizer. Unlike cars that burn gasoline with oxygen from the air, rockets carry their own oxygen supply. The propellant mixture must contain both a fuel source and an oxidizer to initiate and sustain the controlled explosion that generates thrust. The most common type of rocket propellant is liquid propellant, which consists of liquid fuel and liquid oxidizer stored in separate tanks. These liquids are pumped into a combustion chamber where they mix and ignite, creating a powerful explosion that propels the rocket. Section 4. The heart of a rocket, the combustion chamber. The combustion chamber is where the magic truly happens. This is the heart of the rocket engine, the place where the chemical energy stored in the propellant is unleashed to generate thrust. It's a place of intense heat, pressure, and controlled chaos. Imagine a giant, incredibly strong metal cylinder. Inside this cylinder, liquid fuel and oxidizer are injected at high pressure. These liquids mix and ignite, creating a continuous controlled explosion. This combustion process generates an enormous amount of hot, expanding gas. The combustion chamber is designed to withstand the extreme temperatures and pressures generated during this process. The shape of the combustion chamber is also crucial, designed to ensure efficient mixing of the fuel and oxidizer and to direct the flow of hot gas towards the nozzle. Section 5. Directing the power, the nozzle's role. The hot, expanding gas generated in the combustion chamber needs an escape route. This is where the rocket nozzle comes in. The nozzle is a critically important component, responsible for directing the flow of exhaust gas and accelerating it to supersonic speeds. This acceleration of gas is what ultimately generates thrust, propelling the rocket upward. The shape of the nozzle is crucial to its function. It typically starts narrow at the combustion chamber end and gradually widens towards the exit. This converging, diverging shape is designed to accelerate the gas flow smoothly and efficiently. As the hot gas enters the narrow end of the nozzle, its velocity increases due to a principle known as the Venturi effect. The gas continues to accelerate as it travels through the diverging section of the nozzle, reaching supersonic speeds by the time it exits.